prove each of the statements in 23 through 25 in two ways. Part A by contraposition and part B by contradiction. Now, in the last video, we actually looked at this exact statement and we discussed what our assumptions would be for both the contradiction and contraposition. So if you're wondering where I come up with the assumptions for each of these parts, I would reference the last video. For contraposition, we're going to let n be an arbitrary even integer. Then by definition, n equals 2k for some integer k. Now from the last video, I mentioned that the thing that we want to show for the contraposition is that n squared is even. What I'm going to do is I'm going to square both sides of this equality. So by squaring both sides, we get n squared equals 4k squared. Now by algebra, we can rewrite this as 2 times 2k squared. Now since integers are closed under multiplication, then 2k squared is equal to m for some integer m. To wrap everything up, we have n squared equals 2 times m. So n squared equals 2m for some integer m, which means that n squared is even. And that's what we wanted to show for the contraposition. For the proof by contradiction, we're going to assume there exists an integer n such that n squared is odd and n is even. Again, if you're wondering where I came up with this assumption, I would reference the previous video. So now let's unpack these definitions. Since n is even, then n equals 2k for some integer k. Since n squared is odd, then n squared equals 2 times some integer m plus 1. And we have to clarify for some integer m. By substitution, we can plug in n equals 2k into this n in this equation to get 2k all squared equals 2m plus 1. By simplifying, we get 4k squared equals 2m plus 1. We can further simplify this to 2 times 2k squared equals 2m plus 1. Now keep in mind the goal is to find a contradiction. We're almost there. Since integers are closed under multiplication, 2k squared equals x for some integer x. So 2x equals 2m plus 1, which means that an even integer equals an odd integer. That's a contradiction. And so if you notice, everything here is logically valid. We made no algebraic mistakes. So the only mistake we could have made to arrive to such a contradiction is if our assumption is false, meaning that the original statement is true. And so we're done. Thanks everyone, and I'll see you in the next video.